Good morning, everybody. Oh, my mic's muted.
Good morning.
I'm Kyle Davidson. I'm part of the sales and marketing team here at Productive Plastics. With me, I have Robert Browning from the McConnell Co. They're a premier heavy gauge thermoforming consultant. Look forward to chatting about multi-part assembly today. Wanted to thank everybody for attending. Looks like we have a great turnout, and we have attendees from all over the world, such as Turkey, India, Germany, and Singapore. Our goal today is to help you understand application, process, and feasibility when considering thermoforming for multi-part design. We know your time's valuable and appreciate you spending yours with us, so we'll do our best to add sustaining value. Today, we're going to be covering vacuum versus pressure forming, material considerations, does the application match the process, attachment methods, a little bit about tolerancing, and finishing. We expect this webinar to run from 45 to 50 minutes with some time on the back end for questions. There's a lot of topics to cover. Robert could easily spend 45 to 50 minutes on any one of them. So please feel free to ask questions along the way via the Q&A button. Looks like a text bubble with a question mark at the top. We'll try to get to every single question, either live or offline. A little bit about Productive. We're a family-owned company on our third generation, founded in 1955 and based in Mount Laurel, New Jersey. We're a lean manufacturing company with 6 production thermoforming cells with CNC trimming, in-house paint, tooling design, and value-added assembly. We are ISO 9001 certified and especially committed to quality and on-time delivery. Our core values are to honor God, develop people, strive for excellence, and grow profitably. A little bit about Robert Browning. He's the CEO of McConnell Company. They're a premier heavy gauge thermoforming consulting company. He has over 40 years experience in thermoforming. He has 11 patents with 2 pending related to thermoforming and has worked with notable companies such as John Deere, Ford, NASA, McDonald's, Disney, Yamaha, and Sea-Doo. He's often published and is a guest lecturer at companies and universities across the world. We at Productive are very thankful to have him here today. And with that.
Good morning. We're here today to talk about thermoforming and part assemblies. But first, I want you to know, what is the future of thermoforming? I'm assuming most of you, if I ask what is 2 plus 2, you're going to say 4. But what plus what equals 4? And basically, it's unlimited possibilities. And because of that, thermoforming today and the future is just that. We've got unlimited possibilities in what we can do with our thermoforming process and products. It's important to remember that thermoforming is not an art form. Thermoforming today is a science, and for it to be successful, all aspects of it have to be understood and treated as a science. As Einstein said, you have to understand what you're doing, and if you can't explain it to a 6-year-old, you don't understand it. And so we want to make sure that everyone has a good understanding of thermoforming and what can be done with it. What is thermoforming? Well, put simply, the term thermoforming refers to a plastic molding process where a sheet of polymer material is heated to a set temperature and then formed onto a mold. The material then takes the shape of the mold when it comes in contact with it and cools. The molded part is then normally trimmed to make a usable product. In addition, there are many other differential aspects in the thermoforming process, including whether the mold is positive or negative, how intricate is the mold, what finishes are required, and also what materials are used. Thermoforming today in North America is more than an annual $10 billion industry. But basically, what are the advantages of thermoforming? Well, we have low tooling costs with significant savings up to 90% in comparison to injection molding. We got a wide range of material selection and colors compared to most other processes. We've got suitable for just-in-time production strategy. We've got the ability to make large parts, so a wider design scope is available. We've got process and material optimization for cost effectiveness. We got so many things that we can deal with, but we have lower tooling costs with savings up to 90%. That we have the advantage of dealing with these parts. We have cost and time savings. The thermoforming process requires a relatively low level of forming pressure, so tooling can be constructed less expensively and faster than tooling used in other processes. We have design flexibility. We have alternatives to steel and fiberglass parts. We're environmentally friendly. We have in-production enhancements that we can put into our parts as we're working with them. Low cost and fast prototype development, flexible and adaptable to customers' needs. We're competitive advantage from flexible tooling design. We've got extensive options for finishing, patterns, and textures. And we've got short lead times. In some cases, we have finished products in just 4 to 6 weeks. This shows a heated polymer sheet as it comes in contact with a mold. Vacuum is applied, and the part forms under the mold surface to cool and then retain its shape. That's thermoforming in its very easiest basic form. This video basically sort of shows you what thermoforming is. It shows you that we can use a variety of materials, a variety of finishes with different textures. We can even do distortion printing in some cases of what we're wanting to form. But basically, a sheet of material is put in, it's heated, and then it's formed into the shape that we want to form it into, where it's allowed to cool and retain the shape of the part. Now, it's important to remember, in thermoforming, what is commonly called vacuum forming, we do not form our parts with vacuum. Vacuum is only used to remove the air from between the polymer sheet material and the mold to allow ambient air pressure of about 14.6 pounds per square inch to push the material onto the mold surface. So it's essential that we've got good vacuum to be able to remove the air fast between the sheet and the mold. If the vacuum is not correct and the air cannot be removed fast enough, it'll leave marks and defects on the formed part, such as in this image. On this part, by repairing the vacuum system, no other changes were made in the thermoforming process. This part went from this to this. It just shows you that every aspect of the thermoforming process has to be controlled and treated as a science. This is the thermoforming process. Shows the body of a golf cart being thermoformed. It's a large, deep jaw thermoformed TPO part. The part required approximately 1,500 gallons of vacuum to remove the air in the mold and between the material and the mold to be able to make the part. Also, we have to make sure in the forming process we're dealing with color, clarity, the gloss, with every aspect of the part that we're forming. Basically that was an OEM golf cart, Yamaha golf cart body, and it's made out of TPO material. It has a low CTE, or coefficient of thermal expansion. It's got molded in color. It's got high gloss with excellent impact strength. It has tight tolerances for on the assembly line fit. Sea-Doo jet skis, again, it was replacing compression molded and fiberglass parts. The hull and the deck are both thermoformed with molded in color for scratch and higher impact resistance with excellent UV resistance. It has tight tolerances, and the tight tolerances are required for fit and assembly between the multiple parts and the components, including a snap-on bumper around the perimeter. Tractor hoods and engine covers. These thermoformed parts offer greater impact resistance to nicks and dents, as well as being rust resistant, while providing lighter weight parts for better gas mileage. In addition to engine cover, the roofs and many of the interior components are also thermoformed. This cab top incorporated molded in mounting brackets and air ducts, as well as being color matched for a Class A top surface finish with a black textured bottom. Now, I'm not sure how many of you have been in the backseat of a police car recently, and there's really no need to respond, but many police cars today are now using a rigid one-piece thermoformed back seat, as well as thermoformed door panels, seat backs, roof panels. The rear seat areas are now basically vandal-proof, so when the police need to clean their cars, they can just open the rear doors and hose out the back seat areas. Now, an MRI machine, going from one spectrum to another, an MRI machine requires large, high-quality, high-detailed thermoformed parts. Multiple parts make up these machines with a mixture of regular thermoformed and pressure-formed components. Most of the parts are large in size, thus it is not feasible to make these parts with any other molding process. So what's the difference between vacuum forming and pressure forming? In vacuum forming, vacuum is used to remove the air between the polymer sheet and the mold, and then we allow ambient air pressure to push the material onto the mold surface. Now, in order to produce parts with greater detail, pressure forming is used. And pressure forming is where a positive air pressure is applied on the opposite side of the sheet in addition to the vacuum forces. And as you can see in this image, we have the mold on the bottom, and then you have a pressure box on the top side. And in the second image, it shows the sheet is trapped between the pressure box and the mold, and air pressure is applied from the top and vacuum is applied from the bottom at the same time. And in doing this, we can achieve parts that have, sharp details, undercuts, molded in names and logos, as well as texturing that will pick up right off the mold surface. Now, this chart on the right shows you how we can form into sharper edges and undercuts and certain, and get better detail on our parts. Now, the drawback to thermoforming and pressure forming is we normally only get details on one side of our part. This image shows a part and how ribs and vents can be pressure formed. The vent holes are then machined open from the back side, creating a look resembling an injection molded part. Injection molding is accomplished with high pressure, injection molding is accomplished with high pressure because injecting the hot resin into a mold, it creates internal stresses in the parts. One advantage of thermoforming is to be able to form parts with minimum internal stress, thus making a stronger part. In the case of these images, we're able to form undercuts, vents, recesses for logos, sharp details. Pressure forming allows for forming ribs down to 100,000ths of an inch, opened by machining on the back side of the part. This is another example. This is a medical product, and it shows there are formed vents that were formed in with pressure forming, and they were machined open from the back side. And again, the part closely resembles an injection molding part. Pressure forming allows for multiple parts to be formed with close tolerances for fit and uniform finish between the parts. Pressure forming allows for forming undercuts and molded in details with tight tolerances. These two images just show examples of pressure formed parts that are made up of multiple components. Speaking of multiple components, this is a complete thermoformed dashboard assembly for large RVs and buses. All the parts you see are either single sheet, pressure formed, and/or twin sheet thermoformed for a uniform finish in texture and fit, including soft touch materials. Most of the interior parts of these large over-road trucks are thermoformed, including the bunks, the storage compartments, the door panels, and even in some cases, the complete dashboard assemblies are all thermoformed. If you get the chance to get up inside of a truck, it's amazing what they look like inside. This is a replacement thermoform hood for the Ford F-150 truck. This is an as-formed part. So we're able to give you high gloss, high detail, high finish parts. Now, this is a unique pressure formed part. This is an example to show there are many ways to solve issues and be creative with the thermoforming process. This is a mid-size Ford utility delivery van. Ford wanted to offer a panel to go behind the driver between the cab and the cargo area for security and protection, and the panel needed to match the other interior panels. However, since this panel would be seen from both sides, it needed to have the same texture and finish on both sides of the part. In addition, the part required tight tolerances for the fit and alignment of pre-drilled holes in the metal frame. The tooling to injection mold this part would be cost prohibitive, so thermoforming was the logical choice. So how do we get the needed details and texture on both sides of the part, on both sides of the material in the part we're forming? It was decided that TPO material would be the material choice due to its low coefficient of thermal expansion and the high quality finish. To accomplish the requirements for this part, it was decided to texture the mold with the same texture finish as the extruded material. This way, the smooth side or the back of the material would be pressure formed onto the mold, forming the texture into the material. The thermoforming process was tightly controlled to be sure the texture on the front and the front side of the sheet and the back side, they were the same and the texture did not wash out and they stayed uniform. This shows the thermoforming machine with the mold on the top platen and the pressure box on the bottom of what we were forming these parts. The parts exceeded all the requirements and the texture was a perfect match on both sides of the part. This shows that there are many ways to solve issues and create unique ways to meet customers' needs and requirements. So what materials do we use in thermoforming? Well, we have a wide range of materials, including, and probably the most used in thermoforming is polyethylene. We use polypropylene, ABS, styrenics, PVCs. We use thermosets, polycarbonates, TPOs. So we have a very wide range of materials that we can use, especially compared to other forming processes. In the thermoforming process, we use material which has been extruded into a sheet form. The extrusion process has greatly improved over the past decade, and the quality and consistency of material being extruded is at an all-time high. Today, we have many new choices of materials and blends of materials to meet the needs of clients. But we need to remember, though, the extrusion process is an added cost for thermoforming when compared to injection molding and other processes. But with sheet extrusion, we're able to get blends and other aspects of material which the other processes cannot obtain. For thermoforming, we're able to use materials with cap layers, UV layers and additives, co-extruded blends of materials, additives for impact and tensile strength, in addition to textures and colors. The extrusion processes are better controlled than they've ever been to be able to analyze and control the blends and mixtures of the polymers and resins. This extrusion line in the images you see, they produce materials for automotive parts and also for flat screen TVs, which require constant monitoring and the highest level of quality with no distortion or blemishes in the materials. So depending on the parts to be thermoformed, many factors have to be considered to be sure the correct material is used for the project. These include, we have to look at impact, flame requirements, what are the UV requirements, what's the volume of the parts to be made, the formability, how's the part going to be formed, is it a deep draw part, what are the part finishes, is it painting, is it gloss, is it molded in color, are there coefficient of thermal expansion requirements, is it mating up to other parts that are thermoformed, or the mating up to metal parts? What are the tolerances? What's the part usage? So we have to look at many, many different aspects when we're deciding on a project and the material to use. Now, the materials that we use for thermoforming are broken down into two basic categories. That we've got amorphous materials and crystalline materials. What are the differences? Well, both crystalline and amorphous materials are both high temperature polymers. The difference between them lies in their molecular structure. Now, before we decide what type of material to use, though, we need to get a better understanding of both of these. So basically, amorphous materials, they have a random, I'm going to repeat that, they have a random order of molecular structure. Thus, these materials have good hot strength characteristics. The advantage is less energy to bring them to forming temperature, and they're faster to cool. But a disadvantage is that they're going to always have a tendency towards creep or movement. These materials include acrylics, polystyrenes, polycarbonates, PVC, ABS materials, very common materials that we use. Now, the pros to amorphous materials include the facts that they're easy to thermoform, they process better and less likely to warp. Amorphous materials also offer high impact strength and are best suited for structural applications. The materials also bond well with adhesives. They tend to offer part stiffness and strength. Now, a negative or a con is these materials are more sensitive to stress cracking, and they don't perform as well as wear components, and they have poor fatigue resistance. Now, crystalline materials are just the opposite of the amorphous materials, as they have a very orderly group of molecules. The amorphous had a random group. The crystalline materials have a very orderly group of molecules. And by doing this, this allows advantage of good stiffness and low creep. but the parts have a tendency for high stress and warpage. Again, these parts that we're looking at are mainly polypropylene, polyethylene, PET, TPOs, nylons, in this family of materials. The pros of crystalline materials is these are very tough plastics and they have a strong intermolecular forces. They perform extremely well in wear applications for bearings and structural loads. They also provide excellent chemical resistance where amorphous materials don't. What are the cons to this? Is the sharp melting point on the crystalline polymers make them more difficult or more challenging to thermoform. And these materials also have a tendency to be less stable, resulting in dimensional instability compared to amorphous materials. So once we have the part design and the material selection, we then have to identify the correct thermoforming application to match the process. So we have to look at this from the standpoint of what is the design of the part, what is the selection, the client's requirements for the polymer material. Then we look at the design and construction of the tooling or the mode to be able to form the parts. And then we look at the process or forming and finishing of the part. There's a lot of different ways that we can form parts depending on the needs and the requirements. Just to show you an examples, the outer covers of these refrigeration units you see in trucks are made up of both single and twin sheet TPO thermoform parts. These thermoform parts have to be resistant to impact as well as high heat, extreme cold, and UV. These parts have molded in color and will not rust as the metal panels did in the past while being lighter weight. The next time you get on an airplane, look around. Most everything you see on the inside of an airplane has been thermoformed. The seat backs, the tray tables, the storage bin doors, the overhead panels, window panes. Again, due to the lower production numbers and the need for quick changes and variations between the different airlines, thermoforming is the logical process. Now, NASA built 6 space shuttles, but only 5 were actually flight worthy. These shuttles had many thermoform components and parts on them. It's also interesting to see images from inside the International Space Station and recognize thermoform parts that we know have been formed inside and used on the space station for lightweight. So in making a project successful, everyone has to work together and everyone has to participate, and communication is a key issue. The client, the thermoformer, everybody has to have clear communication to make things successful. I like this. This is the definition of an engineer. An engineer is someone who makes precise guesswork based on unreliable data provided by people with questionable knowledge, never wrong, and likes tables. And I think that sums it up pretty good. And, I include myself in that category. Now, to illustrate a communication breakdown, this is an email from a client last year asking for help with their thermoforming project. We responded to their email with questions to get a better understanding of what they were doing and needing. So we asked, what is the material? What is the part and material sheet thickness? How many parts are you needing over what period of time? And do you have any existing tooling? The email was sent. After a couple of days, the client sent back the following email. The material is plastic. This does not help, and this does not help with communication on a project. We have to have good communication. John Deere incorporates as many polymer parts as possible on their equipment for weight and cost reduction, for greater impact resistance, rust protection, and ease of installation. These parts, include side panels, engine covers, cab roofs, and interior cab components. These the painted metal parts and the thermoform polymer parts are mated together. Therefore, the color as well as the fit and finish are critical. In addition, the correct material had to be selected for impact strength and for thermal expansion between the metal and the polymer parts. In choosing the right application and process, many times the thermoformer has to be creative. This particular thermoforming process is what is known as a reverse draw plug assist forming. And this is used to help maintain a uniform material thickness as well as forming complex parts and shapes. As you can see in the image in the upper left, we have a mold on the bottom and we have a plug assist on the top. And generally the plug assist is also inside of a pressure box. that once the material is brought in contact with the mold, air pressure is blown into the mold, causing a bubble to be blown in the material. When the bubble reaches the desired height, then the plug assist and the pressure box will then come down and seal. Air pressure is applied from the side of the plug assist and vacuum is applied to form the part. Now, there you can see in the image on the left, you can see the mold is on the bottom. You have the plug assist on the top, and we have the pressure box. The video on the right-hand side is showing where the material is coming out of the oven. The mold is coming up, it comes in contact with the sheet material. Air pressure is being applied, and you can see the bubble being blown on the material. When it reaches the desired height, then the plug assist and the pressure box come down. It will seal. At this point, the vacuum is being applied, and air pressure is being applied from the side of the sheet. This is held until the part is allowed to cool in the mold. At that point, the mold opens, and you have a formed part. Now, this shows the formed part before and after trimming. This part was designed with formed-in hinges and other components to be formed on the same mold at the same time. Note the texture on the image on the right on the part. That image was formed in the material from texture on the mold itself with pressure forming. This part is actually a cover for a cleaner that runs up and down on a bowling alley. And the part was designed to withstand chemicals and high impact while being a high quality part. I also thought it was nice of the factory workers to color coordinate their outfits with the parts when they were forming and cleaning them. Now, most cars today have simulated wood or carbon fiber or even turned aluminum finishes as part of their interior components. Have you ever wondered how they make these parts? Well, the wood grain is only on the surface of the part, but it's very tough and resilient. In most cases, these parts are thermoformed. It's a thin gauge thermoform with the desired finish. They're laser trimmed for close tolerance, and then they're placed back into an injection molded mold for the ribs and the bosses and the attaching systems to be molded onto the parts. These type finishes are not possible with most other forming processes. So after we formed our parts, how are they attached? How are multiple thermoform parts mated to each other? How are parts attached to metal parts and to frames? Well, we've got adhesive with glues and bonding. We've got inserts for attachment and added strength that can be bonded in and attached to the parts, mechanical attachments, nuts and bolts, and in some cases, a snap fit. Now, on TV and in movies, during a shootout, the police will hide behind their car doors. We all know the doors in the cars today would not stop a bullet. Therefore, a company has developed a thin bulletproof material which can be laid on the door, and then a thermoform cover is put over it to make it bulletproof for most calibers of ammunition. The panel is thermoformed with the same finish and high gloss factor as the painted car finish, what fits over the outside of the door. Now, it's hard to even see the panels on the door unless you're looking down the length of the car and notice the panels stick out about 2 centimeters from the original panels. The panels were initially held onto the car with high-powered magnets. Now, the biggest issue with these panels when they first started using them is when the police would park their cars and go eat or walk on a beat. When they came back, often the panels were gone. It was then that the police discovered that the homeless people, especially in New York, found out about the panels, and they were stealing them off the cars to use them as shelter. The panels are now screwed on in 6 places around the perimeter. There are many ways to attach our thermoform parts. In some cases, especially for large parts, such as panels on the sides of buses, where a clean, smooth surface is required with no exposed fasteners, double-sided tapes are often used. On most of our cars today, tapes are used for attaching, vents, trim panels, and pieces. The Porsche Macan is just one car which uses double-sided tapes to attach the thermoform carbon fiber panels to the doors and the bumpers. This part is the TPO truck cab front cover with critical cosmetic requirements. These parts offer lighter weight for improved gas mileage with greater impact strength. The parts will not rust, and they have dramatically reduced the costly repairs and warranty claims of the previous metal and fiberglass parts. The parts were also designed for ease of installation using tapes and minimum fasteners. In many cases, medical products are not high volumes, or they are designed and used for testing. Due to the many advantages, thermoforming is often used to make the prototypes and low to medium volume production parts. These parts are pressure formed with high tolerances and are machined for fit and finish. In the images you see now, in this case, the threaded inserts are actually molded in and encapsulated into the pressure formed parts during the forming process. This is another example of a very unique pressure formed part. This is the medical device made up of 3 different pressure formed parts with molded in logos and graphics. You can see there's the top, there's the bottom, and there's the front bezel. The part is pressure formed, capturing some of the threaded inserts in the forming process, as well as having additional threaded inserts applied in secondary operations. If you'll notice in the image, the front bezel, it has an undercut and a return lip on the inside of the edge. And what this is for is the 2 halves of the unit will then capture the front bezel. But these parts are designed with a snap lock fit. The snap parts are machined and bonded in place in secondary operations. And due to the many unique aspects is the way that the 2 bodies sandwich and trap the front of the part. Rather than trying to use screws or bond the front housing on. And so we're able to do many different things with our processes. And this shows the thermoform part in use on a thermal retention medical device for thermal management of electronic units. Now, ATM machines. Normally, you would not think of using a thermoform panel for the front of an ATM machine. However, the client wanted the look and finish gained by pressure forming the formed parts, as well as having parts which will not scratch and rust. The parts are bolted-on material for chemical resistance, flame resistance, and impact strength and UV stability. This shows the back and front of the formed part before CNC trimming. Note again, we have molded in details only on one side of the formed part. However, due to this being an ATM machine, additional security was required to prevent vandalism and theft. Therefore, a heavy gauge stainless steel panel was bonded to the inside of the part. The metal insert has the hinges, the locks, and the attachment components. Now, it's necessary to mention here the importance of understanding all aspects of the process. The client specified the adhesive to be used to bond the metal and the thermoform part. The parts looked excellent and met all the requirements. However, when the parts were shipped by air with rapid temperature changes, some of the parts cracked and the metal backing inserts came loose. The different coefficient of thermal expansion of the metal and the bolter run were calculated and compensated for in the design. However, the selected adhesive did not allow for the expansion and contraction between the parts. It's important to remember that every aspect of a project has to be considered to make it a success. In this case, we changed to a different adhesive which will allow for the thermal expansion between the parts. Now, this is called the J-Bell Badger. This is the robot used in stores, especially grocery stores, to monitor inventory and prices of goods. The robot is made up of several large, complex pressure-formed parts. To attach the thermoform parts after they've been precision CNC or robotically trimmed, they're placed in fixtures for exact alignment of attaching blocks to be added to the inside for screw hole and for bonding of the parts together. These parts are thermoformed using Kydex material, and these images show the 2 halves of the robot, the interior and the exterior parts before assembly. And you can notice on the middle image, there's blocks that have been glued on and bonded on for attachment. This video shows the robot in use. Now, these are used in grocery stores, so they will come in contact with customers. So they had to have the highest quality finish as well as safety factors. The assembled panels closely resembled injection molded parts due to the finish, the fit, the texture of finish on the outside of the parts themselves. But these units laser go up and down and will monitor prices and the goods of inventory. Now, before Blockbuster went out of business, they started to compete with the Redbox DVD dispensing. This was a very complex unit due to the multiple parts being distortion printed and then thermoformed. The front of the units were PET and were backlit to make the machine stand out at night. While there are many unique features, I'm only going to concentrate on the main control bezel. And this bezel contains the monitor screen, the credit card holder reader, and the dispensing mechanism. Now, once the parts were formed and trimmed, they were placed in fixtures where attachment blocks were bonded in place. These parts could not have exposed fasteners on the outside of the unit. The attachment blocks were pre-made with threaded inserts. There were also covers for speaker hose and components for drainage of any water which could get into the unit from while they were exposed on the outside. This shows the front and back of the formed parts. Notice on the right-hand image, notice the added on attachment blocks and additional components added on to make the part, structurally sound and to add the monitor and additional components needed. The Marcus Autism Center is in Atlanta, Georgia. The Marcus Autism Center is experts with early detection in children. But they said they can now identify children with autism as early as 18 months old. But many children, unfortunately, are not diagnosed until they're 4 or 5 years old. An ongoing study developed at the Marcus Autism Center is using high-tech pinpoint images to measure intricate changes in an infant's brains through eye monitoring movement for early detection and treatment. Now, the Marcus Autism Center needed a medical unit utilizing their software and detection process. Due to time restraints, I'm not going to go into detail on this unit, but let's just say there was an extensive design process to make this unit ready for prototype testing and production. This unit has 3 computers, 2 monitors, and had to meet all the medical, ADA, and UL requirements. It was decided to pressure form all the parts to make up the unit. Again, there could be no exposed fasteners. The material had to be able to withstand chemicals, bodily fluids, especially from children, impact, and meet the high quality standards expected from a medical device. Kydex was the material selected to make the thermoforming components. This shows examples of hidden fasteners and again, pressure formed vents where they're underneath and out of sight and they're not visible on the part. Now, there are also undercuts in some areas to accommodate the internal electronics and components. And to do this, we actually were pressure forming. Again, all the parts are pressure formed, but we pressure formed the parts to form the undercuts to accommodate the electronics and the needed issues. Now, this shows the internal metal structure and fitting of the thermoform parts. The thermoform parts had to have the attachment blocks bonded in place. And then some of the threaded inserts had through hose as well as additional screw hose to screw it on. And you can see this shows, the blocks on this part, the blocks where they're glued on, and it also shows the narrow, deep draw forming issues we had with these parts. In addition, these parts were fitted with a special extrusion to seal and make the parts together and provide additional strength. You can see the extrusion is between the housing of the parts, especially for sealing to prevent water or anything getting into the area where the computers are. In the end, this unit is made up of 11 large thermoform parts, which all had to match up with very tight tolerances. The finished quality of the parts had to match as well as having uniform material thickness. This was the challenge with some of the parts which had narrow, tight, deep draw areas. Now, this shows the finished assembled units, and these are the actual final production units, and they had both painted and molded in colored parts. So, for a project to be successful, we have to make sure we're dealing with a knowledgeable thermoforming company who knows how to manage a project and meet all the requirements. What requirements do we need to consider? Well, how do you convert a concept to a thermoform part? You've got to manage CAD files. We've got to look at design parameters, radii, draft angles, draw ratios, undercuts, wall thicknesses, part strength. What's the texture? Is the sheet texture? Is the mold texture? Are they both? What is the material selection? What are the tolerances? How is the part going to be trimmed? We have to look at design process. What are the due dates and the review dates that are required for these? In our processes today for part finishing and tolerances, we also have the tools for non-destructive measuring of our part thicknesses, as well as handheld spectrophotometers and gloss meters to measure color and consistency between formed parts. For direct fit of parts on the assembly line, for mating parts together, trimming requires very tight tolerances. Every bolt hole and every edge has to be perfect. This is just showing an example of a CNC robot doing trimming. Companies are required to have this to be able to accomplish the needs of the customer. To emphasize the degree of trimming which thermoforming companies are doing today, this company produces OEM automotive parts. This video shows robotic trimming of a 2-up pressure-formed wheel fender well liner for the Ford F-150 truck. These parts have to be correct. Ford knows that they make approximately $16,000 profit for every truck that comes off the assembly line, and they are producing 1 truck per minute. Therefore, if the parts are not correct, even missing 1 screw hole, and the assembly line is shut down, Ford will bill the company responsible $16,000 for every minute the line is down. But this just shows the complexity of what we can do with trimming and our movement and automatic loading of trimming and forming the part. Now, in conclusion, just when you think you've seen and know everything about thermoforming, let me show you something new and unique. So what do you think this is forming? Would you believe that we're now thermoforming chocolate? Up to a 5-color chocolate screen print can be printed for whatever graphic is required, and then it's thermoformed in the shape of a donut. Many companies bake their donuts, so when the donuts come out of the oven, they're hot, and the donut topper are put on top of the hot donuts, and they melt and stick to the donut. But the donut does not distort the graphics. So how many donut toppers do you think Dunkin' Donuts and Tim Horton would need per day? Would you believe approximately 840,000 donut toppers per day that need to be thermoformed? In conclusion, we have to remember the design intent needs to match the process. We've got considerations to be included are tooling configuration, material selection, color and texture, the thermal expansion, bonding and attachment. And remember, better process controls equal better repeatability of our parts. I want to thank y'all for coming today, and we hope you've enjoyed it. We'll answer some questions now, but we want to get your feedback as well. So if you'll please scan the QR code and take the 1-minute survey, we'd be very grateful. But if you have any questions now, we're going to try to answer those for you.
Thanks, Robert. Wanted to get to some questions. So first one from Jared. Can you define the thickness required to be considered heavy gauge?
The general category is that heavy gauge is 40 thousandths and up, and thin gauge is generally 40 thousandths and below. Generally because materials that can be put onto a roll will be roll fed, and the heavy gauge, materials that are less than 40 thousandths, even with our clamp frames that we're using, they can have a tendency to slide out of the clamp frames. There are special clamp frames that we have and can be made to hold thinner materials, but generally it's classified at 40 thousandths or up for heavy gauge forming.
Thanks for that. So is the mold itself heated or cooled, or is just the material general?
Let me clarify this in a couple of different ways. I'm not saying you cannot form parts on wood molds and composite molds, because we do it every day. But in order to achieve the best parts with the highest quality, we need temperature-controlled aluminum molds. These molds are controlled with temperature, generally with water that is connected to a thermolator. We know our forming process, to use ABS, for example. We know that the optimum heating temperature for most ABS materials is approximately 320 degrees F, that we know the set temperature where it will retain its shape is approximately 180 degrees F. Therefore, we want a mold temperature at approximately 165 to 170 degrees F, because we want it just below the set temperature, so it will still allow the material to slide over the mold, but yet it will cool down below the set temperature. The molds being heated will allow the water flowing through to pull the heat out of the mold to allow the part to cool faster. Whenever we form on wood or fiberglass or composite materials, it takes much longer for the parts to cool, and we have a greater chance of forming in chill marks, thinning, and less details on the formed parts. So yes, the molds, you generally want to use temperature controlled molds if possible.
Thanks for that. I have a question from Anonymous. Could you clarify if Kydex or PVC acrylic materials are amorphous or crystalline thermoplastics?
It depends on the blends that we're using. The Kydex materials, there's certain blends that they can fall into either category. And so we look at different things when we're looking at these. And so to answer that question, you'd have to go back to the actual chemical compound of whether it's a Boderon, whether it's the Kydex, and the blends that we have into the materials, and the additives that we add into it, because it actually can change the process as we're getting into it.
Thanks for that. I have a few questions about this. Could you describe twin sheet thermoforming?
Twin sheet thermoforming is basically where I'm having two modes. I have a mode on the top, and on my top platen, I have a mode on the bottom platen. I will have generally it's on a 4-station rotary machine. So I've got, I have a heating state, I have a load unload station, I have a heating station, a second heating station, and a forming molding station. The mode, generally what will happen is the first sheet will rotate into the twin sheet in the mode set. The first sheet will rotate into the forming station. It will form onto the bottom mode. The sheet is released from the clamp frame. Then the machine will rotate and the second sheet will rotate in, and it is formed on the top mode. At that point, the two modes are then brought together. They're locked together with what we call bayonets on the perimeter around the outside of the platens, and then airbags are inflated like in the pressure forming process, which will seal the modes together. So basically we're creating a hollow part in most cases. We can put inserts in between the two sheets of material, but in most cases twin sheet is a hollow part. Advantage of twin sheet formings is that we can use different colors of materials, we can use different thicknesses of material, we can even use different types of materials in some cases. But if you want to contact me, I will try to explain that in more detail with images and from that aspect. But we just didn't have enough time to go into twin sheet forming in this webinar.
Yeah, but we'll provide Robert's contact information on the last slide. So Robert, does the mold designer, I know it's kind of a loaded question, but do they compensate for the mold for a CTE? Is the part will shrink as it cools?
In most cases, I'm going to say no, because the thermoformer should be dealing with the client and dealing with the material supplier to know what the expansion and contraction, the thermal expansion of the material is. The tool maker is generally going to build his tool with the aluminum shrinkage that they would calculate into it. Now, the better tool makers will also work with you based on past experience, where they know how much TPO, certain blends of TPO will shrink and grow. They'll also deal with, based on past history. So I'm not going to say they won't, but they would prefer you to come back to them and tell them what the amount of shrinkage is. It's just a liability factor more than anything else. But a knowledgeable thermoformer from past history and from the geometry of the part should be able to give you a close indication of what that thermal expansion is going to be. This is a loaded question that people ask, and it's something that you have to be sure you're dealing with qualified people. So when we look at this, knowing where the material is thinning on the part, where there's thick areas in the part, because you have to remember in thermoforming, when we form our part, the thin area is going to cool first and the thick area is going to continue to shrink. So we have to understand on our tooling how to control that and also where the thermal expansion is going to take place in the part. So you want to make sure you're dealing with a thermoformer that knows about it and also the sheet supplier. And again, communication is the key issue between all people involved with the project. So everyone has to be able to communicate equally on this. The tool maker does not want you to send them a drawing and say, build me a tool. That's the worst nightmare thing you can do because they don't know what you need. They don't know where connections need to be. They don't know what machine you're going to put it into. But many times a tool maker will get just a drawing that says, build me this tool. And that's the wrong way to go about this because you're going to just have trouble from every aspect.
Thanks for the answer. It's kind of a good segue into our next question. What kind of questions should you ask a thermoformer when considering a multi-part project?
One of the main ones is their past experience. You want to ask them what is their machinery that they have. You want to know what are their machinery capabilities. Is it straight thermoforming? Is it pressure forming? Basically, I hate to say this, but you want to find out how old the machines are for repeatability of the parts, as far as the movement of platens and things like that. Then you want to find out on their trimming, what type trimming. Are they doing hand trimming, hand routers? Do they have 5-axis CNC? Do they have robotic trimming for the parts? How familiar are they with secondary operations for attaching mounting blocks, for attaching components? And then does your part require additional work? Does it require, in addition to bonding, does it need painting? What is the finish requirements as far as packaging? So basically you need to be asking these type questions to the thermoformer, and then also what materials that they're familiar with. And, it's one of these things you want to deal with a knowledgeable company that has the experience to be able to handle your parts.
Thanks for that. Couple more questions. I know we're running right up to the hour. For pressure forming, do you recommend amorphous or semi-crystalline plastics?
You can use both. But generally we find we get better parts with the amorphic materials, just because the crystalline materials have a greater tendency for warpage and bowing. And whenever we're forming the parts, with pressure forming, in a way, we're forcing the material into undercuts. We're forcing the material into sharp corners. And the crystalline materials just do not like to do that. And they will have a greater tendency to lose those details into edges will be rolled edges more than the sharp edges that you're going to form. So generally we find we do it more with the amorphic materials than we do with the crystalline, but that's not saying we cannot do it. It's just going to, again, depending on the design and the geometry of the part and what you're looking at. There's not a rubber stamp for the thermoforming process. That's one of our advantages, is that we can look at things from many, many different directions and many different ways. In doing the design of this, as I've tried to show you, we have multiple ways of forming parts. And so we have multiple ways of doing this. So it's just finding the thermoformer and understanding the best way to make the parts for you.
Great, appreciate that. Two more questions. Can parts be painted with a separate painting process at our manufacturing plant?
I'm assuming you're saying, can the parts be thermoformed by one company and then sent to you and painted? The answer to the question is sure. You can send them to a third party. You just have to remember, what is the material that you're painting? Because if you're trying to paint most crystalline materials, the paint's not going to stick to it. Polyethylene, polypropylenes, you have to do corona fire treatments and things like that to get things to stick, and they're always going to have a tendency for easy being scraped off. Most of the time, the parts that are painted fall into the categories of the amorphous materials. But yes, thermoforming companies, I know, Productive Plastics, here they have where they can paint the parts for you. Other companies will bring them in-house and paint them themselves, or they will send them to a third-party operation.
Got it. And the last question, Maddie is asking if you have any sample donut toppers.
Actually, I do. And actually, I'll tell you this, the chocolate is actually Dutch chocolate. The chocolate is interesting because it's brought in from Europe, and it's brought in tankers that resemble a gasoline tanker truck where it's pumped into the facility. But it's a very interesting, very unique process. Again, it just shows you thermoforming has unlimited possibilities. That who would have ever thought that would be thermoforming chocolate?
Well, thanks everybody for attending the webinar. We hope you found it valuable. So we can continue to deliver this type of content. Please, it's really important that you help us by filling out the survey. After the survey, we'll give you links to download some of our guides to thermoforming. So that's design guides for thermoforming as an alternative to sheet metal, fiberglass, injection molding. The replay will be hosted on YouTube in the next couple days, and we'll send that out to you. And
I appreciate your time, and I hope you found it enjoyable. And if we can help you in any way, let us know.
Thanks so much, everybody.
Thank you.